So in the last developer conference, we talked about compliance and requirements that module developers would need to take into account to bring modules to market. So where would you start if you wanted to figure out how to establish module compliance? The requirements would be a good place. So look on the left. I'll run through them. The MDK is your most comprehensive reference for the module development requirements that Project Ara imposes. You might also need to look up FCC requirements. Carrier terminal specs would apply if you're looking at a module that needs to work in licensed frequencies. Finally, modules may require other kinds of certification and regulatory assessments for approvals, depending on the type of application that the module addresses. For instance, a module that has medical applications might need to look at regulations around Part 18 of the FCC regulations, or even FDA regulations. Or if a module is available for operation in the EU, then we might need to look into CE specifications. Next, you might ask, what would it take to get a module authorized? So there's two parts to this, one that we're looking at for the market pilot, and the other for a scaled launch. So for the market pilot, because we have about 20 to 30 modules that we're looking at, Project Ara partners are going to work with you, work with module developers to help to get modules authorized. You heard about some of this earlier. Actually, several people mentioned the kinds of things they're doing. They're building test equipment, custom test equipment, defining test protocols that are very specific to the Ara platform, and everything is built around specs that test MDK compliance. Now, depending on the module and the type of application, we expect that this process is going to take anywhere between 3 to 8 weeks. It's an iterative process because you're looking to develop and then test and build compliance. Google is also planning to get special temporary authorization from the FCC for the market pilot. And finally, on the carrier side, we're working with carriers, OpenMobile and Claro, to develop a tailored terminal acceptance process for our devices. Now, what about global launch? That's going to be a much larger set of modules. And we would like to transition to a process that's really powered by module developers. Now, what does that mean? First of all, the MDK specifies Project Ara requirements. And module developers can either test in-house to demonstrate compliance, or we're envisioning the use of third-party labs to help with this process. For FCC authorization and carrier acceptance, third-party test labs and accredited test labs would be the way to go. I'd like to walk through a little bit. I talked about MDK compliance requirements, and I'd like to walk through a few examples. So first of all, MDK compliance requirements fall into two broad categories. The first set of requirements is at the module level, and these cover a host of specs, environmental, mechanical, and power management. Actually, I heard a number of questions, and really, we're addressing all of them in the MDK. That's our goal. The requirements that are environmental in nature are thermal, around temperature, humidity, electrostatic discharge, vibration. I'll talk a little bit about it. I'll give you some examples. The ones around mechanical requirements, I'll talk about those too. Those are very specific to the Ara platform, and I'll give you some feel for what we're looking at and how we're testing it for compliance. There's also requirements that are electrical, around voltage sweep, input and output noise, power draw and discharge. So I'll talk a little bit about these requirements and how we're testing them with a few examples. Okay, the system level requirements at the network, software, and operations level. For the network, we're talking about requirements for MFI compliance, Unipro compliance, and the Gray Bus compliance. I'll talk about it with some examples. We're also looking at software requirements for Android and the kernel. And then with operations, there's wake, detect, and hot plug. So there's, I saw several speakers earlier before me talk about these requirements, how they're built, and what the platform does. But really, the MDK is where you would go to look at the specifications and how you would test for it. Electrostatic discharge. So this is something that we've all experienced, right? You walk on a carpet, touch a door, and you feel contact discharge, right? And you could also experience it when you come close to something that has these electronic components. So we're using a pretty standard set of specifications. It's the IEC 61000-42. And this is a set of specifications that characterize a typical ESD event, electrostatic discharge event, either when you come in contact or when there's an air discharge, right? And it's in the context of all mobile phones, laptops, computer devices. In the case of Ara modules, the discharge locations are module-specific, right? But they include sensitive areas like the interface block, module part lines, and so on. Now, how do you test and measure compliance? Really, what you want is when you have an electrostatic discharge event, under the operating conditions that we specify, you really want functional operation to be maintained, and there should be no damage after an ESD event. So vibration testing. Now, vibration testing is typically required to ensure that there's structural integrity and functional integrity. The MDK requires vibration tests to be performed typically 5 minutes along each orthogonal axis at 30 hertz and a 0.06-inch displacement. Now, after the vibration tests, again, you need to perform visual inspection for structural integrity, and you also need to test for normal functional operation. What do we use for tests? This is pretty standard, electrodynamic shaker tables with control software. This is what you would use for these tests, right? So, and that's really what we're doing as well for all the prototypes. Okay, now for mechanical fit. This is, again, very specific to the Ara platform. So first and foremost, modules would need to be manufactured to the technical specs in the MDK. This includes the 3D CAD models that we provide, the 2D line drawings, color, material, and finish specs. And how would you test? Really, it's about measuring tolerances. So an optical measuring tool is what we're using. And you need to compare these tolerances for what's in the MDK and verify compliance. Okay, electro-permanent magnet hold, right? Now, you heard Ara Kanan. He talked about EPMs, and he also showed some pictures of some of the test equipment we're using. When you talk about EPM hold compliance, modules must first conform, again, to the material and the geometric specifications in the MDK. And this includes all applicable tolerances, right? That's the first thing. It should be manufactured to spec. And then we want to make sure that the modules themselves remain attached to the endo. And we have two sets of requirements. One is when the modules are attached in the attached state, and they're in the detached state. So 15 newtons per interface block is what we require, and 3 newtons in the detached state. Now, how do we test for this? In Ara's talk, I saw him show some of the pictures, and here's a representation as well. There's a specially designed electromechanical pull tester, which really tries to separate the modules from the endo, right? Applying force 1 Newton increments at a time until there's a release of the module. But we expect those limits of 15 newtons per interface block and 3 newtons for attach and detach to be maintained. I talked a little bit about network compliance, and really we're relying on the MIPI specs, right? Conformance test suites that are in the MIPI spec, whether it's the M5 or the Unipro test spec. For layer 1, it's M5. And when we look at the transport or data link or network layers, really we're looking at the Unipro spec. And the MDK has the exact version that we're referring to. And we're using standard MIPI conformant protocol analyzers for this purpose, testing against the specs and making sure that the protocols are consistent with what the spec defines. OK. Now for the requirements around RF emissions. I think I heard some questions earlier on the day, came in for one of the panels, but I wanted to talk a little bit more about this. At a first cut, the MDK, the specs actually require that every module has a shield. And this is placed over all active electrical components. This prevents users from simply touching the modules, right, and hurting themselves just touching sensitive components. But it also acts as a Faraday cage. So for all non-emitter modules, they look pretty much equivalent from an RF perspective. Now, in the United States, the FCC has adopted and used recognized safety guidelines. And this is for evaluating RF environmental exposure. The exposure limits used by the FCC are typically expressed, you heard people mention it, SAR. This is specific absorption rate. And there's also measurements around electrical and magnetic interference. So this is field strength and power density. And this is for transmitters that operate anywhere from 300 kilohertz to all the way to about 100 gigahertz. In addition to EMI, which is electromagnetic interference, and SAR, there's also requirements that the FCC has with respect to hearing aid compliance. And another set of requirements falls under the broad category of electromagnetic compatibility. Now, what this really means is a set of requirements that govern a system's ability to function in the presence of electrical noise. And this is something that could be generated internally by one of the modules or externally. So EMC compliance is something else that's required by the FCC. Where would you go for FCC requirements, or if you wanted to figure out what's necessary? There's a code of federal regulations, and really Title 47 is your most comprehensive reference for it. The FCC has specific requirements for certification of RF emitter modules, and subpart J in part 2 is where you would go. I've listed some of the measurements here that are required, but there's an exhaustive description of what you would need to do. This is a topic of interest, right? Specific absorption rate. So what is it? It's really a measure of the rate of absorption of RF emission energy, RF by the body, right? And there's a safe limit, 1.6 watts per kilogram of human tissue, really measured over 1 gram of human tissue, would ensure compliance. And compliance for SAR must be met before any device is out there in the market, and FCC approval is granted for marketing a device like this in the US. How do you determine SAR values? You determine it by measurement. But we're doing something else in addition. We're also looking at simulations, computational models, and we're looking on really getting accurate simulation data from these computational models. We're conducting, for our Spiral 2 and Spiral 3 prototypes, we're conducting both measurements and computational models and simulations, really, comparing the two towards FCC compliance of our 3G and 4G modules. You'll hear a little bit more about this. The next speaker, Ted, who goes after me, is going to be talking about computational modeling and the work that Metamorph is doing to build simulations with OpenEMS. And these models really are built with a number of components. CAD models that we have from the MDK. There are CMF specs, antenna models, and we combine all of these with a set of libraries from Metamorph to then build models that we use for simulations. What are we doing in terms of the OpenEMS simulations and industry standard simulation and modeling tools? We're really working to calibrate them for both simulated RF emissions patterns as well as absorption we're training these simulation models with a known set of configurations, and then using blind testing to validate them, right, and test the accuracy. Our goal is to really refine the accuracy of these simulation tools and make OpenEMS available to developers. So if you wanted to estimate and calibrate and see how far you are from the requirements, you could use these tools. And then you could, of course, always do measurements, right? So the measurement for the authorization process is always there. But the OpenEMS tool is really there for you to assess compliance. So what about the market pilot? First of all, Google will obtain a special temporary authorization to test Ara modules in the field. We anticipate having a pretty small number of emitter modules, right? So it's not big for the market pilot. And for each RF emitter module that needs to be authorized, the goal is to conduct both a set of measurements and simulations for all the configurations involved, right? Involving other modules as well, whether it's intentional radiators or unintentional radiators. And what we'd like to assume there is that the impact of non-emitters is really not going to be significant for EMI or SAR. And all these locations of the non-emitters are equivalent. Now, measurements, we're going to be conducting these measurements, and we've started work on this for the Spiral 2 prototypes with accredited labs, and the test results are going to be submitted to the FCC for approval. Okay, so all through this talk, I've tried to point out, some of these areas which are really specific to Ara for modules and configurations that apply to Ara. And to give you a sense for the number of configurations that need to be tested, I just have an example there, right? So if you're looking at 10 possible locations for modules on the endo, and you had 3 emitter modules, 2 of which you were using in pairwise combinations to really evaluate SAR, then the number of configurations is large. It's 270, right? Would you be testing in all of these configurations? Now, there could be some simplifying assumptions that would help us reduce the complexity. Really, if SAR contributions are additive, or if the non-emitter positions are equivalent, then that number reduces significantly, and it's down to about 28, much more manageable. Now, for global launch at scale, right, if we had to look at a much larger number of modules than we would have for the market pilot, testing configurations with every combination of emitter and non-emitter modules could end up being pretty complex and also expensive. So here's what we're proposing, the concept of a gold master emitter module. Well, what does that mean? This could be a module that's a gold master is tested exhaustively, right? And all the configurations with a set of other modules that forms a baseline configuration, and it's authorized by the FCC. That's a set of modules that we would do exhaustive tests, all configurations, all slots, generate these measurement results. And then if you had to now take the gold master out and substitute it with an emitter module that needs to be tested with the same parameters, of course, if our measurement results for one set really end up being as good or better than that emitter module, then what we could do is really work with that set of measurement results and then simulate all other possible configurations, right, with our simulation tools. And that's what we want to do to actually see, how can this help us to exhaustively evaluate what that emitter module does in the context of all the other modules that are there. And this is work in progress. We'll keep you updated. This is something that we're building, the capabilities that we're building. We're testing these out as we speak. Another interesting topic around carrier terminal acceptance. So, I heard questions about how we're going to go about this. Really, the carrier terminal acceptance requirements for a module depend on a bunch of different factors. The first one of them is the radio access technology. Is it 3G? Is it 4G? What kind of technology is behind that? That's gone into that module. The second is, what frequency bands are we operating in? And the third is the kind of services we support, voice, data, SMS. There's a whole series of them. Now, typically with carrier terminal acceptance, there are lab and there are field tests. And these tests are really about validating radio and physical layer characteristics, looking at protocol implementation, right, of the access technology, and then network performance. Are they complying with the throughput requirements that the carriers have for operation in their network? So towards the whole process of carrier terminal acceptance, we're going through it in a few phases, right? First of all, for experimental testing of the Ara 3G and 4G modules that are there in our Spiral 2 and Spiral 3 prototypes, we're actually working with carriers to get licenses to do these tests, right? And T-Mobile is working with us, and you also heard about OpenMobile and Claro for the experimental testing. Now, for the market pilot, we're taking a route where we're looking at non-stock devices, and these are devices that are not stocked in carrier stores, but these are going to be in our food trucks, right? And we're developing a tailored acceptance process. We're really looking at their requirements, their broad set of requirements in detail, and looking at those requirements that are applicable just to the Ara modules, and working around all the sets of constraints that we need to look at in the context of Ara. Now, this includes a bunch of things: pre-provisioning, management of subscriber profiles, account activation, that's a big one for the market pilot, and logistics, right, involving other Ara partners as well. We're also looking at running performance tests, protocol verification, and some of the stuff around network access and connectivity. We're working with third-party test labs to see how we can build that test acceptance process, the tailored one, and have modules ready for the market pilot. And finally, for launch at scale, really we're looking at a set of terminal acceptance and protocols and procedures that will apply not to just non-stock devices, but you'd also be able to sell these devices in carrier stores. So it would include stock devices as well. Okay, and I think with that, I've come to the end of my presentation. It's been pretty long, so thank you. Thank you.